Back to the Hong Kong Symposium, Science for the Future. We now come to the Mathematics and Computer Science section with the theme of Shenzhen Hong Kong Cooperative Innovation. Now, please welcome Dr. Henry Shum, Rotating Chair, Council of the Future Forum 2022, Adjunct Professor, Tsinghua University, Forum Member, U.S. National Academy of Engineering. Dr. Shum is the convener of the Mathematics and Computer Science section, and he will introduce the section using a recorded video. Dr. Shum, please.
Good afternoon， 大家下午好，欢迎来到我们数学与计算机科学深港合作创新之路的 session。数学与计算机科学是科学与技术发展的基础。Computer science is the new math。几乎所有的交叉学科的基础研究都与数学与计算机密不可分。未来科学大奖对数学与计算机科学奖的设置，其实就体现了对这两个领域的基础性以及前瞻性价值的高度认同。推动数学和计算机科学在粤港澳大湾区开花结果，就是我们这一场讨论的意义。我们这次 session 设置了3个主题报告和1个对话环节。我先来介绍一下我们3位主讲嘉宾。我们第一位嘉宾是2018年未来科学大奖数学与计算机科学奖的获奖者，台湾清华大学教授与半导体研究学院院长，台清大与台积电联合研发中心主任林本坚教授。林教授的创新开拓的浸润式微影方法，革新了集成电路的制作进程，使得先进半导体芯片的特征尺寸能够持续缩减为微纳米量级。在过去的15年以及可预见的将来，为建造最强大的计算与通讯系统做出了关键的贡献。林教授的演讲题目是DK1 光刻技术展望。我们第2位嘉宾是来自斯坦福大学计算机系开放式虚拟助手实验室主任，美国国家工程院院士 Monica Lam 教授。林教授的主要贡献包括设计出已被应用于所有的高性能机器学习芯片上的收缩阵列架构和软件，以及计算机编译优化。他是享誉全球的编译器技术专家。我们学 Computer Science 的学生应该都读过林教授的 Compilers 的教科书，大家也称之为龙书。林教授也是 Omelette 公司的联合创始人 CEO。他给我们带来的题目是将神经语言模型驯化成值得信赖的绘画虚拟助手。我们的第3位嘉宾是2022年未来科学大奖数学计算机奖的获得者，香港大学教授、数学研究所所长、香港科学院院士莫以明教授。莫教授因为创立极小有理期限组 VMRT 理论，并用以解决代数几何领域的一系列猜想，以及对自存组上的 X Chanel猜想的证明，荣获2022年未来科学大奖数学与计算机科学奖。莫教授将以负微分几何的功用为题，以具体事例展示负微分几何对代数几何及数论的应用。在我们的对话环节，我们非常荣幸地邀请到未来论坛理事、启明创投主管合伙人梁颖瑜女士担任主持嘉宾。她将与深圳科创学院发起人、香港科技大学李志香教授、香港特别行政区政府创新科技及工业局局长孙东教授、深圳市科创委主任王友明博士，以及我本人共同探讨深港合作创新之路。接下来，让我们一起期待本场嘉宾的精彩发言。谢谢大家。
Thank you, Dr. Shum. Now, let us welcome Professor Bern J. Lin, President, College of Semiconductor Research, Taiwan Tsinghua University, Director, NTHU, TSMC Joint Research Center, Member, Taiwan Academia Sinica, Member, American Academy of Engineering, the Future Science Prize 2018, Mathematics and Computer Science Prize laureate, to deliver his keynote speech under the title of Outlook for Low K1 Lithography. Professor Lin will deliver his speech online. Professor Lin, please.
Well, ladies and gentlemen, it's a pleasure to be here. I'm glad to present the outlook of low K1 lithography at this symposium. Let me share my presentation. Okay. Well, lithography is a key technology to enable shrinking of feature size and increase of circuit density for semiconductor integrated circuits. K1 is an indicator of the ease to use a given imaging system. The smaller, the more difficult. The next slide shows the resolution and depth of focus. The resolution is represented by half pitch. As a function of lambda, the imaging wavelength, and theta, the aperture angle of the imaging lens, and K1. And this is what we'd like to talk about. And the available minimum half pitch can be scaled down, of course, by reducing the wavelengths or by increasing this theta. Well, it can also be manipulated by K1, but K1 is not just a simple coefficient. To manipulate this K1 needs a lot of technologies and innovations. Well, there are, as I mentioned, there are several ways to improve this half pitch. One is to increase the lambda, the wavelength. Well, here I say lambda sub 0 is the wavelength in the vacuum. And n is a refractive index. These two combine to give you the wavelength in the media. And then this is sine theta. So there are four ways by increasing the theta, reducing lambda sub 0, or increasing n. Here, we like to concentrate on the reducing K1. Well, what does K1 mean? K1 means the natural distribution of K1 is from 0.8 to 0.28. For K1 equal to 0.8, it's very easy to produce a beautiful image. K1 equal to 0.28 is pretty tough. The image will look awful. But if you can make sense and take advantage of it, you are able to use given lambda, given sine theta, to a new, smaller half pitch. Well, usually for people who are familiar with microscopy, we know that its limit is about 0.61. And for lithography, its limit is almost limitless. I'm going to show you today up to K1 equal to 0.07. Okay, well, what good is it to have to reduce K1? Well, if you successfully reduce K1, you don't have to spend any more money getting new wavelengths or a new lens. This, we're talking about tens of millions of US dollars. This is similar or even more. Okay, you don't have to change the mask technology. In doing so, you may even increase the depth of focus, which will show in the previous equation that depth of focus will decrease when you reduce the half pitch. Now, by reducing K1, there is an opportunity to increase the depth of focus. However, the key is we need innovation to do that. It's not as simple. It's not a simple drop of the number on that equation. Okay, I'm going to show you one technique that can reduce a K1 by half. That is called two-beam imaging. Two-beam imaging is, this particular two-beam imaging is called off-axis illumination. All you have to do is to tilt the beam in your illumination. Okay, here, I'm showing a grating on the mask. When the half pitch of this grating becomes smaller, the diffraction angle, this is the 0th order diffraction beam. These two are the first order, +1 and -1 diffraction beam. Of course, we have the higher order, second order, third and fourth, and so forth. We only show the first order beam because that is what lithography cares about. If you need to use the higher order beam, that means you are wasting money. Okay, so in this case, I'm showing first order, 0th order and 2 first order beams, and these 2 first order beams exceed the acceptance angle of this lens. What it means is that these 2 vectors do not go through, only this goes through, and this one is just a 0th order beam. It carries no information. It only changes the intensity of your image. All right, so what do you have to do to capture all these 3 beams? You can make this lens larger, right? Make it larger so that the angle will accept these beams. But that's not the requirement here. The requirement is that you have to keep the lens the same without changing your theta of the lens, but you have to make it resolvable. So off-axis illumination means I'm going to tilt this illumination by such an angle so that those 3 beams are now shifted like this. You can now capture the 0th order beam and the -1 order beam and lift this out, or you just have to lose this beam, but you have these 2 beams. Now it's what we call two-beam imaging. If you want it to be more symmetrical, you can also add another beam here, and you are throwing out these 2 beams, but you're keeping these beams to give you an image. Okay. The catch is that if your angle is not ideal, here I'm using an ideal angle. If your angle is not ideal, you may have some complication. The beams may not line up in these 2 directions. It may have multiple directions and give you some complications. Okay. Now I'm going to show you analytically what's happening. So we'll put in numbers. Theta sub 0 is the 0th order, is the optical axis, okay, is 0. And then that is the tilt of this 0th order beam here, theta sub 0. As a result, your theta 1 is this, and your theta -1 is this. Sine theta 1 is equal to sine theta plus lambda over p, and this is minus lambda over p. That's how we describe these parameters analytically. Okay, now this gets a little bit complicated. I want you to know that I'm interested in the intensity of this distribution, and the intensity would be the electric field of these 2 beams, the 0th order and the -1 order beam, plus the same beam again, but this is a conjugate. So the conjugate of this electrical field with the electrical field becomes the intensity, which the photoresist, the photosensitive component of the resist will only recognize the intensity. It doesn't recognize the field. All right, now we have the intensity, and we'll go through all the calculations, and we'll have all this. Okay, we come up with this this relationship here. This is a general equation describing the intensity. And if my theta sub 0 is equal to this, theta p over 2, then we got a lot of simplifications, and we end up with this intensity equal to the magnitude of the 0th order beam and -1 beam and the plus minus 1 beam plus the magnitude multiplied by cosine of this thing. Then there's no z dependence. This is only dependent on x. That means you have information in your image area, but you don't have a z dependence. That means this beam goes on indefinitely. You have infinite depth of focus. Okay, what a beauty it is. You just by tilting the beam, you get infinite depth of focus, and then you double the frequency here, 2kx. You double the spatial frequency. So you are reducing k1 by a factor of 2, and you gain also an infinite depth of focus. All right. Okay. So that helps you to reduce k1 by a factor of 2. Let's say if we can comfortably operate k1 equal to 0.6, now you can operate k1 equal to 0.3. So that is quite a great improvement. However, the limit lies at k1 equal to 0.25. No matter how much you do, you cannot exceed, because this is a physical limit. You cannot exceed k1 equal to 0.25. But I just told you that we can reduce k1 to less than 0.25, much less than 0.25. We can reduce it all the way to 0.07. So let me introduce another k1 reduction technique to go that far. So that is we further reduce k1 by halves. That means we can now reduce k1 by another half. Let's say if we are at k1 equal to 0.28, we use this technique, multiple patterning technique, we can reduce the k1 to 0.14. If you apply the same technique again, you can have 0.07. Okay, now let me explain what's going on. What we want to do is we have two patterns. Okay, at the larger k1, and the feature size are also bigger. These two have the same feature size and the same k1 distance and so forth. However, if you do a double exposure or double patterning, then you're combining these two patterns into this third pattern, and you see they complement each other, and you end up with a regular array, much smaller pitch. Also, if you use some shrinking technique to shrink the feature size, you end up with this, which you couldn't do before. Let's say if this were k1 equal to 0.14, you could only do k1 equal to 0.28, 0.28 here, 0.28 here, and here would be 0.14. Okay, what's happening? All right, if I don't do anything, you now have an electric field here, and you have another electric field slightly away from the mask. So you have two fields. And of course, the intensity would be the summation of these two fields, right? And then and find the absolute amplitude, intensity. So here, if we have a situation where S equal to 0.75, now don't confuse this with K1. It's not K1. It's just a simple distance. I'm just illustrating this. If you have a distance of S equal to 0.75, these two are distinguishable. And the sum of these two fields will be this. They have less contrast, of course. Here it has a very high contrast. This also has very high contrast, but unfortunately the two are very close to each other. So you have reduced the contrast, but you still can separate the two peaks. Okay. Now, if I reduce S, if I bring the distance closer to simply S equal to 0.66, well, you can no longer distinguish these two peaks. It becomes one Y peak. It's not dissolvable. Okay, that's a situation when you try to sum it up by coherent summation. Okay, how do we improve it? We can now do so-called multiple patterning. We'll do a double patterning. At first, we have this intensity here, this electric field here. and we turn it into intensity. Okay, now this is the intensity here. It's all positive, indicating its intensity. There's an intensity here. I use this intensity to expose the photoresist. And after exposing the resist, I etch the bottom, the substrate, using the resist image. The resist image will be similar to this, using it to etch the substrate. So we have this in the substrate. This is now in the silicon, so to speak. Or let's say we have a silicon dioxide layer. This would be a feature in the silicon dioxide layer. All right, on this wafer, I coat with a new resist. The old resist was removed. It's now clean. It only has this silicon dioxide feature. So I coat with new resist, and I do the exposure again and do the etching again. Since the two etch images do not interfere, they don't have any sensitivity. They are just image topography. So we can put these two very close to each other, okay? And we end up with this, two very close patterns. The S now is what? The now S is, I cannot see it from a slide here. Somebody can see it, maybe. Oh, I see. Okay, no. All right, let me.
Now, you may prepare the questions for the Q&A section. In the Q&A session times, we can have one questions in the Q&A section. You may prepare your questions in English or 普通话, and then our moderator and panelists will answer your question in Q&A section. You may prepare now. For some technical problems, now we would like to invite Professor Monica S. Lam, Professor, Computer Science Department, Stanford University, Faculty Director of the Open Virtual Assistant Lab, OVAL, member of the U.S. National Academy of Engineering, ACM Fellow, to deliver her keynote speech. The title is Taming Neutral Language Models into Trustworthy Conversational Virtual Assistants. Professor Lam will deliver her speech using a recorded video. Mr. Lam, please. Professor Lam, please.
All right. Well, thank you. Greetings from Stanford, California. Thank you for inviting me. I'm really glad to be able to speak to this audience. It's too bad that I won't be there in person, but I'm really looking forward to this winter because I get to come home to Hong Kong for the first time in 3 years. What I'm going to talk about today is how we can tame neural language models into these trustworthy conversational virtual assistants. This is a really exciting time for computer scientists because the computers is now getting its third generation interface. The first one is the terminal. The second is the graphical user interface. And now we have natural language. Finally, the computer is learning the human language. Voice is the technology behind this visionary video that was put out by Apple in 1987. And what they showed here is how a professor can prepare a lecture without using the keyboard at all. All he has to do is to talk to his assistant. But with voice, we can go way beyond what we normally do on computers. We can now reach people that digitization has left behind. And that includes the blue-collar workers. And because with voice, what they can do is to just talk to the computers on their job and ask for any information that we'd like to get access to. With this voice, we can now get to jobs that require the human touch. And now we are able to help solve the manpower shortage issue, for example, in mental health care. And we can also use this technology to keep seniors company. Okay, we can now talk to them and keep them entertained. So it is a way for us to help prevent dementia and depression. So if you look at what we are talking about now, it is very different from what we have at hand. If you look at Siri, look at Alexa or Google Assistant, this is very different. I mean, this is much more advanced. And because of the technology because of the rate at which the technology has been growing, I predict that we will see socially intelligent virtual assistants by 2030. Why the optimism? So in 2020, OpenAI kind of surprised everybody with GPT-3. It is a very large neural network. It has 175 billion parameters, trained on 45 terabytes of internet text. It can generate a lot of text that is very, very coherent. It can even write college essays. But don't expect to get an A or A plus, from the GPT-3 generated essays. You can get about a C. Now, that's not so bad, isn't it? But this is 2020. And in the last 2 years, there are many, many more models. And now we are tenfold bigger, with Wu Dao going at the 1.75 trillion parameters. This is just incredible. However, we can't celebrate too early because LLMs are known to hallucinate. It actually doesn't know what it is saying. It would say things that are not necessarily true. For example, if you talk to GPT-3 and try to buy a plane ticket, it can tell you that it has bought a ticket, but don't believe it. They are not doing any, it is not buying you a ticket. And nor actually is there a flight, UA-123 that goes to New York. Okay. And the real reason here is that there is really no magic behind GPT-3. It is a statistical machine. It is trained to predict the very next word of input text. It does not know the meaning of the words. In a sense, it likes to speak without thinking. As a matter of fact, we all have some kind of an LLM in our brain. Sometimes when we are tired, sometimes when maybe we have a drink too much, sometimes we are saying things that we don't really mean. And that is because the voice or the speech generation is done by an area called the Broca's area. On its own, it can generate a lot of text, but it is really the prefrontal cortex that helps control the text that is actually being spoken. They provide the inhibition and control. And experiments show that if your prefrontal cortex is damaged, we will just speak without thinking. It was all good sentences, but that's not what we really want to say. So what it means here is that LLMs need external control, and it is not enough just to train larger and larger LLMs. And this is what we're doing. We are creating a language called GenieScript. It is a language, a programming language for writing virtual assistants. With this language, the developer can control what the agents are saying, providing the high-level planning and making sure what is said is truthful. And what the GenieScript program does is provide control to these large language models. And what we're going to talk about today is how do we make these large language models more truthful? If you ask me for information, If I am not sure, what I do here is that I consult these reputable sources. And in the same way, we need to teach the LLM to consult consult these external databases that are kept current and provide good information, in real time. In order to do that, what we have to do is to train or fine-tune these large language models that take natural language and turn it into code so we can access this external knowledge base. And with that, the information comes back to GenieScript, and the developer gets to decide and present the information to the end user. We don't just take the information, to take the input from the user, send it to LLM, and directly give the output of LLM to the users. So we need to provide this extra external control, just like our prefrontal cortex is making sure that we just don't speak without thinking. Right. But the problem here is that in order to fine-tune or machine learn, or train the large language models, we have to have training data. This process is extremely data hungry. You have to provide a lot of training data. But training data in natural language is very expensive. So, for example, a simple sentence like, how far is the best Italian restaurant, translates into this long piece of text. So it is not like you are asking the consumers to label an image, whether it is a dog or a cat. It is not easy to create these annotations. And you have to do it sentence by sentence, domain by domain. And this is very, very expensive. And this is the reason why Alexa has 10,000 developers. And to this point, after the N years that they have been at it, they're able to handle single sentence commands. They are not even conversational. If you want to have a conversational agent, you really need exponentially more amount of data to do a good job. So what do we do? So recently we saw a breakthrough. We have been working on this problem, and we make this one simple observation. And that is, today, if you look at what we do in companies, every company has data and they have a schema for their data, but they don't have to write their own database software. They use the same database software. And the reason is that computer scientists have figured out that regardless what kind of queries that you may have for all kinds of data, you can access them using combinations of just about 6 basic primitives, 6 basic database primitives. And looking at this, we decided that we should try this approach where we're just going to just create one program that synthesizes the training data. Again, we take the company schema and data, we just generate thousands and thousands of conversations about the domain that the company is in, and all these sentences can be created by using a grammar of about 6 primitives and combining them to create these conversations. That sounds too easy, isn't it? The problem here is that when you use this approach, you are going to get these clunky natural language sentences. It's perfectly annotated with the code, but that's not what typically, we say in any of the particular domains. So the solution here is to turn to the large language models for help. These large language models have been trained on, terabytes of text on the internet. It has a lot of domain terminology. So we leverage this. We take that and we convert the clunky natural language into this fluent natural language. And now we get a very large training set, very, very cheaply, that covers all kinds of things that people may say. On top of that, we throw in a few shots of real human annotated data. And typically, I would say about 2% of what people have been doing if we were to do everything by hand. And we take this, and again, we take advantage of the LLMs, we fine tune it, and this is how we can train the LLM at a very decent cost. And this actually covers conversations. So we make all this available in the Genie script language. And here is the entire program if you want to build a restaurant assistant. So here we say that this, if you want to reserve restaurants across, for many, many different restaurants, you need a knowledge base of restaurants, and you have to have an API, an action that will allow you to make the reservation. You provide this information, import it into your program, and you just write this one line, and we automatically give you a conversational virtual assistant. So, for example, this is the kind of code that we can handle, all by you supplying the program we show and a few shots of real life training, real life manually annotated data. So as you can see in this kind of example, it is very, very common for the users to ask for something, and then when they learn what is available, they change their mind and they go back and forth until they finally decide on what they want. If you don't use this approach, if you have to script it by hand, it is very laborious and it is very hard to be complete. But what we are doing here with this approach is that we automatically synthesize this thousands and thousands, hundreds of thousands of these conversations for each of the domain that you care about automatically just from the schema and the sample of data. So that's how we reduce the development cost. So we take the sentences in natural language and we convert them into code. And what I'm showing you here is what the code typically looks like. So with this technology, we have used it to generate a bunch of results. And this is done by just a small research team. But this technology allows us to build these systems at a very low engineering cost. So, for example, we showed that we were able to answer complex questions on restaurants better than, say, some of these commercial assistants. Using this technology and extended it to multilingual assistants, we were able to show that if you give me an English assistant, in one day, we can turn it into an assistant in a new language by doing just a little bit of manual translation. We have also built various prototypes of working assistants. The first that I want to tell you about is Genie. It is the first conversational virtual assistant. It doesn't just take one command at a time. It will converse with you, and it doesn't have all the skills that Alexa and Google have. But we have done the top 10 skills, and it can control about 300 different IoT devices. And we have put it in on, for example, the Baidu speaker. We're thankful that Baidu let us have their speaker as a development kit so we can do our experiment on it. We have also put it on the Raspberry Pi, which allows everybody to have the virtual assistant at home so they can keep the personal information at your own house and gives you the privacy. And it has been distributed with Home Assistant, which is an open source product that allows people to run gateways controlling their IoTs at home. We have also started to look at the desktop computer use cases. We have built a multimodal assistant on top of AutoCAD Forge, and this is for the facilities managers to access information via voice. We have also used this technology to build a social coach. It's a coach that teaches adults with autism how to make friends and how to behave socially. So all these are possible because we have lowered the engineering cost by taming the neural models into trustworthy agents. And our goal here is to make the Genie script available to everybody so as to empower the millions of developers out there. Because I think that there are 20 million GUI web developers out there. We expect to see 20 million voice assistant developers in the future. So in summary here, I want to emphasize that this GenieScript project is open source. I truly believe that it really takes everybody to work together in order to create this really useful NLP technology. And we work together, it will be better than what any single company can possibly do. And our goal here is to get to the socially intelligent virtual assistants by 2030. We would love to have you guys join us in this endeavor, and you can contact me at lam@stanford.edu. Thank you for your attention.
Thank you, Professor Lam. Because of the technical problem, we disconnect with Professor Lin. Now the problem solved. I would like to invite Professor Lin to continue his sharing. Professor Lin, can you hear me?
Oh, yeah, sure.
Thank you. Then please share your PowerPoint and continue your sharing. Professor Lin, please.
Okay. I believe this is where we got interruption. All right. I lost it again. Where was the sharing? Okay, this is sharing. All right, so we, using a double patterning technique, we can put these two features very close to each other before they touch each other. So the S is about 0.4 here. .4 here.
Maybe we can continue later. Now, I would like to invite Professor Aiming Mok, Edmund and Peggy Jie Professor in Mathematics, Chair of Mathematics of the Department of Mathematics, and Director of the Institute of Mathematical Research of the University of Hong Kong, member the Hong Kong Academy of Sciences, and the Future Science Prize 2022 Mathematics and Computer Science Prize laureate, to come on stage to deliver his keynote speech. The title is Complex Differential Geometry in Action. Professor Mok, please.
So first of all, I'd like to thank the organizers for the invitation. I'm a theorist. I do pure mathematics. It's a bit far away from practice, but on the other hand, has been a long time tradition for at least 400 years that mathematicians would set up theory and try to resolve as much as they are and make them available for use in later situations. So other people will take them for practice. So I'm a complex analyst and a differential geometer, but what I'm going to talk about will be something, as you may say, this is application of complex differential geometry to other areas of mathematics, such as algebraic geometry and number theory. Okay, so geometry has a long tradition. It went back to Euclid, 300 BC. And the first thing is about the axioms. There were 5 of them. And essentially, it says what you learn in high school, that through any 2 points, there's a unique line. And through any other point outside, you can pass a line that's parallel to it. And the important thing from there is that it brings in the concept of parallel transport. That doesn't work. Okay, so it brings the concept of parallel transport. This is nothing obvious. If you're on a sphere, you cannot do that. Then comes non-Euclidean geometry. This was Gauss back in the 18th century, and he studied surfaces in R3 and introduced the notion of curvature. The interesting thing there is that there's something called extrinsic geometry and intrinsic geometry. He discovered that if you take the two eigenvalues of the second fundamental form and take the product, there's something intrinsic, and this is now called the Gaussian curvature. Riemann, his student, generalized the notion of Gaussian curvature and built up an intrinsic geometry. And Riemann is really someone who has done a lot of mathematics, although he died at the age of 40. But he introduced the notion of a Riemannian metric. So think about the sphere. So the sphere, you have the spherical metric. But you can have a variable surface like a torus in R3, but you can have something abstract. The important thing is that he introduced, so then here he introduced the notion of a Riemannian connection. This means that you can do differentiation on vector fields. Well, if you have a function, you can differentiate and get the velocity vector, but you cannot differentiate the velocity vector without defining it. And this is the basic thing. And what comes out from this is that there's a notion of curvature. Okay, now this is in explaining what is called geodesic. If you take 2 points sufficiently close to each other, in the presence of a Riemannian metric, you can take the shortest distance, shortest path between them, and there's a unique such a path, and this is called geodesic. So for example, you have the lines, strict lines on Euclidean space, and you can have this great circles on a sphere. Okay, so if you look at the center, for instance, this is 2-dimensional radius from there, and you get polar coordinates. So points are joined to the center by shortest distances. These are the geodesics. So these are very basic notions, and I want to make use of them. Okay, next comes the complex number. Its number square is equal to -1. This is one of the most important inventions in the last 400 years in mathematics. You can embed the reals in the complex, so x plus iy. Important thing is that, one important thing is that over complex numbers, you can always solve. Polynomial equations. So it has n roots. Whereas if you take real numbers, you cannot solve them in general. Everybody knows the quadratic formula. Okay. Now, then what does analysis? Complex analysis. Well, of course, you know calculus, and calculus is one real variable. You try to do something in one complex variable. Then you can introduce the notion of a complex derivative, and this leads to actual differential equations called the Cauchy-Riemann equations. And then if you put a disk is where you can do analysis in one complex variable. If you paste the disk together, what you get is what is called a Riemann surface. Okay. Now, the sphere can be given the structure of a Riemann surface by stereographic projection. You can project from the North Pole, and you can project from the South Pole. Then the intertwining, the change of variable are conformal maps. Conformal is the same as being complex analytic or holomorphic or complex differentiable. So this gives you an example of a Riemann surface. Okay. So the compact Riemann surfaces are classified by the genus. You have genus equal to 0, the sphere, genus equal to 1, and then the higher genus. Now, this trichotomy is very important. So the genus 1, for instance, has different complex structures. So there's a space of possible complex structures, which is in one-to-one correspondence to the set of complex numbers. Okay. So a complex curve is just terminology, is the same as a Riemann surface. A rational curve is a genus 0 curve. Elliptic curve is a genus 1 curve. Higher genus means genus at least equal to 2. Then you have projective space, which is just compactifying Cn. You close Cn up, and this is called a projective space. And then a projective manifold is just a closed complex submanifold. One subject of study of mine is the set of unirule projective manifolds. Think about this very simply as a projective manifold filled up with lines. Henri Poincaré is a great mathematician who was responsible for many discoveries at the turn of the 20th century, including the uniformization theorem. And he was also the author of the Poincaré conjecture, which was solved by Perelman. And this was one of the millennium problems, using the Ricci flow, or the evolution equation. Okay, now what is a uniformization theorem? Uniformization theorem says that the set of Riemann surfaces can actually be classified, completely classified in some sense. Well, there are those which are called simply connected. This is just topology. Every loop can be shrunk to a point. Then there are only 3 geometries. K positive, which is a sphere, K equal to 0, which is the plane, and K negative, which is the disk. And this beautiful trichotomy is at the beginning of a lot of mathematics. Now, the first thing I wanted to do was to try to generalize, at least for the case K positive, in higher dimensions. And this is the famous Frankel conjecture, or generalized Frankel conjecture. The Frankel conjecture says that when the curvature is in some sense strictly positive, this is called bisectional curvature, then it's projective space. And this was a problem solved by Professor Yamtong Xiu and Xingtong Yao. But it was solved at the same time by an algebraic geometer, Shigefumi Mori, by using completely different methods. What I was interested in is a much larger class. This has Ricci curvature positive and bisectional curvature semi-positive. And I solved the problem proving that under those assumptions, then this is a symmetric space, Hermitian symmetric space. A symmetric space has to do with some kind of symmetry on the manifold by holomorphic isometries. So what is interesting in this here is, in some sense, this is interdisciplinary. I'm using 2 sets of completely different methods. One is differential geometry and differential equations. The other is algebraic geometry, the theory of rational curves. And I will just put in the scheme the first two lines there, 2 paragraphs there. So first of all, okay. I have to go back a little bit. Okay. Okay, I have to go back. Okay. So here, I use this equation which was defined by Hamilton, which was again the tool to solve the Poincaré conjecture. But this was before the Poincaré conjecture. I proved that under this evolution equation, the property of having bisection curve bigger than or equal to 0 is preserved. Then I use Mori's theory, algebraic geometry, to say that there is at least one rational curve. And then I deform the rational curve. I deform the metric here, I deform the rational curve here. Okay. And then it turns out that these are filled by the minimal rational curve. These are unirule projective manifolds. And then I use differential geometry and the evolution equation to prove that actually there is an object which is invariant under parallel transport. So here comes the parallel transport in Euclidean geometry and Riemannian geometry. And this is the new object. The new object is here. I look at this special set of lines and look at the collection of tangents. The total set would be called the VMRT. Okay, so from the invariance of the VMRT, and assuming that this is not the whole space, one deduces that this is a symmetric space, like a Grassmannian or the hyperquadric. Okay, so what is a minimal rational curve? A minimal rational curve is just, think about it as a line. So a rational curve is the same as a Riemann sphere. Just insert a sphere inside there of minimal degree. And this is the picture. This is the moduli space or classifying space of all lines, and you have a line bundle over it, a projective line bundle over it, and this is the space X itself. And this is the so-called tangent map. To each line, you associate the passing through X, you associate its tangent. Okay, the first example of a uniroot-projective manifold comes from special relativity. So special relativity is in 4 real dimensions. You complexify it, you have 4 complex dimensions. According to special relativity, light travels along certain special lines. These are the light rays. They are just defined by some equations. Namely, you have something called the Lorentzian metric, and this is the statement that the light always traveled at a constant speed. Okay, if you complexify, then you get what one may call the complex light rays. Complex light rays, when you compactify, are the minimal rational curves. So the hyperquadric is such a one, but if you look at the equation with square replaced by cube, you get Fermat cubics and so on and so forth. These are then further examples of uniroot-projective manifolds. These are very important classes of manifolds, and up to that point, there was no way to analyze these manifolds further than the Mori theory. So we define such a theory. So this just explaining what I said already. These are examples. So if you look at a cubic, look at a hyperquadric example, the Minkowski space, you can get the light cone or the null cone here. And if you get a cubic, then this is a codimension 2 subset, and it's defined by 2 equations, quadratic and a cubic equation, and so on and so forth. So these are rather explicit. So we know the structure of these VMRTs, and so we define a new geometry. So in Riemannian geometry, at each point you have the unit sphere. The unit spheres are all the same. But in the VMRT theory, the models, even the models are different. It varies from point to point, and the geometry is a geometry of sets. It lives in the fiber bundle. Another class which is very important is the class of symmetric spaces, including the Grassmannian, the hyperquadric, and so on. And we have explicit description of them in terms of Lie groups. Okay. So I'm just writing in words what I already said. There's something called the minimal rational curve, and then at each point you can define the tangent map, which just gives the tangent to a minimal rational curve. And the picture we had before, the universal family, this was constructed abstractly, but if you assign the tangent to a point in a curve, you get the image inside the projectivization of the tangent space, and that's called a VMRT. That's the embedded picture. So it looks like this. If I have something of Picard number 1, then you take 2 arbitrary points. You can join this point by a chain of rational curves. So the intuition is that a minimal rational curve looks like a geodesic, except that like here, you have such geodesics only in certain directions, not in all directions. But you can join them by a chain of geodesics. So this gives you the intuition. And this geodesic serves as carriers of information from a point to another point. And then you can look at the picture here and transport the information all the way. So you can localize it at an open set. That's the principle. Okay, so this is a question that I raised in 2008. This is actually after a lot of years of theory already, and this is called the recognition problem. The recognition problem asks, for instance, for G mod P, for rational homogeneous spaces of Picard number 1, whether you can prove that the space is the model by just looking at one point. So this VMRT serves as something like a landmark, or like biomarkers of an organism. Okay, so this is a question. And I proved this for the symmetric and the contact case, and then Huang and Hong proved it for the long root case, but the proof of the general case was only finished in the last couple of years. The important thing I want to introduce here is just these first two lines, that there's the notion of parallel transport, even for this geometry without metrics. In Riemannian geometry, you use the metric to do transport. Here, you don't have the metric, but there's still possibility of doing parallel transport. Let me skip what's here and just come back to the picture. Okay. Okay, so this is parallel transport. Okay. Now what's happening here is that you have a curve, and then you can lift this curve to this fiber bundle of VMRTs. And then there are these vectors which are just tangent to this VMRTs, and you can talk about the second fundamental form. These are like the second fundamental form defined by Gauss. The statement is that you can transport this vector to a vector here. You can identify vectors along here. And this was not expected. You can do this. And therefore, information about this is carried to this. So it says that the information at the central point would look like this. So for instance, if this is a quadrate which is non-degenerate, and this would still be non-degenerate, and then the whole quadrate would be non-degenerate. So the non-degeneracy would be preserved by parallel transport. And that's a key observation. And the recognition problem was actually done after this theorem was proved that I made with Jimok Huang. Perhaps I would just skip this and give you the picture. So here's a picture. So this is called deformation rigidity. So in mathematics, you model things on manifolds. And very often you study their deformation. And the question is whether mutation can occur. That is, whether something can suddenly change to something else. So if this does not happen, then we call this deformation rigidity. We do it in the framework of algebraic geometry. Everything is projective. And then the principle underlying the recognition problem was to say that, well, this is a landmark, or this is a biomarker. If the biomarker does not degenerate, then the manifold does not degenerate. So you recognize a manifold by one point. And at that single one point, this VMRT is smaller, the dimension is smaller, then you can do induction. And the first theorem was to prove that this indeed holds true in the symmetric case. In geometry in general, that's also correct. It's in a chain of 5 different articles that Huang and myself. But then there's one particular case when deformation rigidity fails. And that's precisely when the VMRT can jump. So when the VMRT mutates, then the manifold mutates. Okay, this is another principle which is easier said than referring to the words there. It's a local to global principle. We found that for this VMRT geometry, if you have a local map which preserves the VMRTs, then it's a global map. This in physics would be called causality. So something happening in a small open set dictates what happens in the whole manifold. And that's an important principle which we call the Gardon-Fubini principle. And by means of this principle, we solve the famous Lazarsfeld problem. Namely, this is something about maps. If you have G mod P or Picard number 1, and you have a map from Y to a smooth projective manifold, then there are only 2 possibilities. Either this is a projective space, or this is an isomorphism. And we use just the local to global principle. This is a theorem that I obtained with a former student of mine. This is about passing from the analytic site to the algebraic site. So you can define substructures like Riemannian submanifolds. And for Riemannian submanifolds, you have total geodesic spaces, and there's an analog here. These are the unary projective varieties. And we found a sufficient condition for this, and which is described in terms of distribution. So the statement is this. If certain non-degeneracy conditions are satisfied, we prove that actually this open set S, this is just a subset, a submanifold of an open set. This can be continued to a submanifold of X, and X is projective, so this is algebraic. So something analytically defined is algebraic, so that's the important point. So there are local conditions of non-degeneracy which can be checked by linear algebra, which proves that something that's only locally defined is global. Now then comes to genus 1 situation. Genus 1 situation, I'll be doing number theory instead. So the elliptic curves are just C mod L, so the complex plane mod L by a lattice, and the lattice can be defined by a point in the upper half plane. So a lattice is generated by Z and a point in the upper half plane, but two different tau may define isomorphic the elliptic curves, and this condition is well understood by mathematicians, and this is the relation. They are isomorphic if and only if they are equivalent under a substitution where A, B, C, D are all integers. And this gives you the SL2Z. The quotient of this turns out to be isomorphic to the complex plane. So this is a moduli space of elliptic curves. And this is given by the J function. The J function is explicit. There are defining equations for the elliptic curve, and J function is expressed in terms of this invariance. So this is explicit. These coefficients are obtained by summing over the lattice. And this gives you a modular discriminant. So J is a function which identifies this quotient with the complex plane. This is completely transcendental. It looks like the exponential function. The exponential function that you learned in high school days, but you just define it for complex numbers. But then J is from the upper half plane, not the whole complex plane. But it has features looking like the exponential function. This is the fundamental domain. So if you mod out by SL2Z, the set of equivalence classes is like this going to infinity, and there's a point at infinity which corresponds to the point in infinity of P1. So this is C, and then you add a point at infinity. It's a one-point simplification. Okay, now then I want to talk about Shimura variety, which is the topic of my second main contribution. You can talk about not just C mod L, but instead you look at Cn mod L. So there's a typo here, it's C to the power n mod L. Topologically, you're just taking copies of the circle multiplied together. In the case of the curves, it's just two circles. Here, they consist of 2G circles. Okay, and this gives you what I call abelian variety. They are principally polarized in a technical sense. And then it's again Riemann. So Riemann introduced the Riemann bilinear relation, which says that this tau must satisfy the symmetry condition and the imaginary part being positive in order to define an abelian variety. An abelian variety is C to the power n mod L, which is projective algebraic, which can be put into projective space. Okay, and this defines what is called a zero upper half plane. And the zero upper half plane is equivalent. This is a zero upper half plane with the Riemann bilinear relation, and this is equivalent to something which is bounded. Okay. And then you have something which is analogous to the J function. You quotient out Hg by this SP Gz, you get the Ziegel modular variety. So this is the analog. This is a Ziegel modular variety. A lot of mathematics is over this topic, works of Fuse Medalists and so on. So here are the balanced symmetric domains. So the type 3 one correspond to the zero upper half plane, isomorphic to zero upper half plane. And these classical ones are very much studied by the late Professor Hua. In fact, his State Natural Science Prize first class was revolving around works over this. And then there are exceptional domains. Then comes problems in number theory. In number theory, the Shimura varieties are classifying space of various structures in mathematics, and they are extremely important. So here, Andreae conjecture says the following. You look at the J function to start with. The J of tau, well, you can talk about algebraic numbers. If tau is an algebraic number and J of tau is also an algebraic number, then tau is a quadratic extension, it lies in a quadratic extension. So these are very special points. So these are called special points, but the notion can be generalized to higher dimensions. The Andreae conjecture says the following. If you're on a Shimura variety, it is simply omega mod gamma, like Hg mod SPGZ, for instance, as an example. So if you have an infinite accountable set of points and look at the Sarisi closure, that is a smaller set, algebraic set containing these points, then the Andreae conjecture says that this set must be Shimura's, must be a totally geodesic subset. Okay. Well, actually, more than that, it should be a finite union of Shimura's varieties. But Shimura's variety are exactly the totally geodesic subsets which have at least one special point. And then comes this Pillar-Zanet strategy, which translates questions to this number theoretical questions to questions involving two parts. One part is arithmetic, and the other part is exactly geometric. The other half is geometric. So this geometric component, which is the characterization of Sarisi closures for algebraic subsets. So you take this subset in omega, project to the quotient, and then take the Sarisi closure, and then you would study this Sarisi closure. And this is the Lindemann theorem. The Lindemann theorem says that if this is in transcendental number theory, if you have n numbers which are Q-linear independent and they're algebraic numbers, then the statement is that their exponentials are algebraically independent. The Charnois conjecture is to say that if you take the exponential, you have these two n numbers, then the transcendence degree is at least equal to n. Solving an analog of this problem would solve the Andreae conjecture, actually, if you add also the other number theoretical component. And this is work of Alan Baker, Fuse Medalist, who proved some partial converse of where these exponentials are taken to be algebraic, and then these are shown to be linearly independent over Q bar. Okay, I would just say that then I enter into the picture by doing in the rank 1 case, solving the Ax-Lindemann problem without arithmetic condition, and this is beyond what could be done by number theorists. And the work I did actually was in part based on work that I did with the late Professor Zhong Jiaqing from the Chinese Academy of Sciences back in 1989. Okay. So I will finally just say, well, one theorem. So this is the one statement of the Ax-Charnois conjecture for Shimura variety. It looks like something like the Charnois conjecture in that you're looking at functions that is on omega and then functions that is on omega mod gamma, and you have a statement about their transcendence degree. If you look at the statement this way, it would be very difficult to know how to approach this. But actually, there's a different formulation, and the formulation was this one. This formulation is in terms of intersection, dimensions of intersection. And then it makes it clear that, to me at least, it makes it clear that one should apply methods of complex differential geometry. about the strata on which this extra intersection occurs. This is called unlikely intersection. Then I brought in techniques from algebraic geometry, and then together with number theorists and logicians who have been working on the J function, was able to produce a solution of this problem. And the important thing about this problem is that it has lots of applications. One important application is about solving, finding rational points, the solving system of algebraic equations. The genus 2 case, the genus bigger than equal to 2 case was due to Faltings. This was his work earning him the Fields Medal in 1986. And now lately there was the uniform model length conjecture solved by a number of people, and they make use of the generalizations of the Akshan-Noir conjecture for Shimura varieties. So the result was here. It is given by, well, I didn't mention the names here. These are works of Gao, Habeger, and Dimitrov, so it's here. The names are here. So let me end here. Thank you for your patience.
Thank you, Professor Mok. Please be seated. Thank you. Now comes to the panel discussions. First, I would like to invite Ms. Lisa Learn, Member Council of the Future Forum, Managing Partner, Chi Ming Venture Partners, to come on stage to moderate the discussion. Ms. Learn, please. Also, we would like to invite Professor Dong Sun on stage. Professor Sun, please. Professor Dong Sun is Secretary for Innovation, Technology and Industry, the government of the Hong Kong Special Administrative Region. Fellow, Canadian Academy of Engineering, member the European Academy of Sciences and Arts, fellow the International Academy of Medical and Biological Engineering, fellow of IEEE. Come on stage to join the panel discussion. I would like also to invite Professor Zha Xiangli, 还有 Dr. Henry Sham, 还有 Youming Wang to join us online. Now, I would like to pass the mic to you.
Sorry. Well, first of all, I would like to start in English. I know that our panel is going to be in Mandarin in a little while, but it's great to see that we have such an event in Hong Kong with participation with the Hong Kong Academy of Science and also Future Forum. So hopefully this will be the beginning of many, many collaborations with the Hong Kong Academy of Science. And obviously, I think today it's so overrun. We're seeing that a lot of professors really like to share their research in China as well as globally. So we'll continue to work hard on building that collaboration. 今天非常感谢呢。今天其实我们对谈里边，今天的是数学与计算机科学深感合作创新之路。那我们有几位大咖呢，都在现场，还有在深圳里边，然后还有我们的孙东的局长在现场香港。今天呢，在现场那边有李泽湘，深圳科创学院院长，还有大疆的前董事长。然后呢，我们还有Harry 沈向阳，今天早上大家都听到 Harry 的演讲了，他也是我们未来论坛理事会2022轮值主席。然后呢，就还有孙局长呢。然后线上我们还有在深圳里边的王友明，深圳市科技创新委员会主任。谢谢大家。那就今天因为时间里边有限的，本来我们应该是55分钟，但是今天呢应该大概是35分钟就要结束了，所以我就直接进入话题，还有问题。首先第一轮的问题呢，我会向每一个演讲嘉宾呢都去问他们一个直接的问题，然后后面的如果还有时间的，我们就有每位嘉宾都会回答一两条问题，然后如果还有时间的话呢，我们就希望预留3分钟给要不香港那边问一个问题，然后深圳那边问一个问题吧。好，那第一个问题呢，我们是给王主任的。王主任，世界和中国正处于100年未有之大变局中， 如何在诸多不确定性的中找到确定性，强化创新能力，无疑是重要的战略选择。粤港澳大湾区是中国创新的重要源发地，未来将成为具有全球影响力的科技创新高地。自粤港澳大湾区发展规划纲要发布3年多来，我们切身感受到大湾区各城市之间联通明显加速，科技创新合作、人才融通频繁，国家高新科技企业数量不断攀升。为何短短3年，粤港澳大湾区便可以取得较为可观的成果呢？未来粤港澳大湾区协调发展的重点何在？难点何在？又应该如何破解？有请王主任。
好，谢谢主持人啊，大家下午好。这个很荣幸有机会参加今天这个论坛，也谢谢给我这个发言的机会。刚才这个主持人问了这样的一个问题，我想这个粤港澳大湾区的发展呢，备受关注。这个粤港澳大湾区的发展规划呢，是19年年初这个印发出来的。那么这个9+2城市之间的这个交流与合作也在不断的深化。特别是深港两地之间，这个在科技上合作也取得了一些突破性的进展。比方说，像在科研的这个规则的对接、机制的对接上，这个科技部和深圳市政府也联合出台了一个叫做先行示范区科技创新的这个行动方案，在河套地区推行与香港科研规则相衔接的这个项目经理制度、政企联投制度、选题征集制、同行评议制、定期评估制、团队基绑制等6大科研管理机制。第二个呢是这个深港合作的平台建设，像河套地区这个出台了的这个联合政策包，目前呢这个河套地区推进落地的这些高端的科研项目超过了150个。那么这个梦工厂北区在前海也开源，那么青年创业是吧，也备受关注，有611个团队也在香港创业都还走得比较顺利。第三个呢是创新的要素流动也更加便捷，比如说像深港澳科技计划项目我们财政资金跨境使用现在也都正常化了。这个香港大学深圳医院、港中文深圳研究院这个香港科技大学深圳研究院、香港浸会大学深圳研究院等4家机构呢，也获得了科技部批准成为试点单位。同时呢，像这个科学仪器共享平台路网有1.2万条已经对外开放使用，在香港呢也同样可以注册使用。我想这些成果的取得主要有3个方面的要素。第一个呢是国家层面的这个在战略上的布局，也因为粤港澳大湾区本身就是国家在这个科技领域里面、创新领域里面这个一个重大的布局。那么出台了一系列的惠港、惠澳的政策，你比如说像对港开放了国家研发计划和科技创新2030的重大项目。第二个要素呢是粤港和深港两地政府之间的这个务实的合作，我们设立了13个粤港合作的工作专班，19个深港合作的工作专班，这个工作机制也正常化稳定。第三个呢是创新主体之间这个合作的也更加密切、更加顺畅。6所香港的高校在高新区设立的大学研究院，在累计呢，在深圳设立的香港的有关的科研机构有88家，孵化的企业呢有265家。同时呢，又有5所香港的高校在河套地区设立了科研的这个相关的机构。这个未来呢，发展的重点呢，就是要加快前海、横琴、南沙等这个粤港澳这个重大的合作平台的建设。就我们深圳而言呢，我们将重点在 推进前海、河套2个合作区，一个是现代服务业合作区，一个是科技创新的合作区，积极对接了香港的这个城市战略包括香港北部都会区的发展战略。另外一个呢，就是要探索有利于推进新技术、新产业发展的这个有关的规则、国际贸易规则创新规则，建设河套深港创新合作区、科技特区。现在呢，目前呢，我们也在这个特区规则上在大胆的设想争取得到国家更大的这个专属的跨境政策的支持。关于粤港澳大湾区协调发展的难点呢，我想主要是这个进一步推动这个相关的要素的自由流动。第一个呢，就是通俗的来说，还是就是在体制机制上的软联通，就是因为毕竟香港和内地之间还是一国两制，还有很多的这个科研、法律、税收等管理制度在有两地之间还是有区别的，所以我们想在这个推动这些规则进一步衔接有利于释放科技人才的这种交流与合作的积极性。第二个呢，是推动基础设施的硬联通比方说像这个香港保税区的这个1号通道的改造等等第三个呢，是深化科技产业的合作，因为这个科技资源呢深港两地之间互有优势，如何发挥这个两地之间优势互补，联合一起就深港两地之间一起来开展核心关键技术攻关，共同推进大湾区国际科技创新中心和这个综合性国家科学中心的建设，打造更加有国际竞争力的现代产业体系。因为我们知道深圳的现在这个无论是高新技术产业也好，创新的这个生态也好，是吧？这个应该说涌现了一批像华为腾讯等这种创新型的企业，同时呢，这个众多的中小企业也是这个雨后春笋般的诞生。所以深圳的这个创新生态，全过程创新生态链的这个会不断的催生深圳的这个创新的企业的诞生，创新人才的聚集，创新成果的这个涌现。所以我想在将来我们将进一步加大力度跟香港之间推进这种科技创新上的合作。我就讲这么多，谢谢。
好，谢谢王主任的分享。下面呢，我也希望跟问一下李教授，因为毕竟李教授在深圳里边也非常成功的创立公司。那科技创新不是一两个技术创新的问题，需要大量的企业用扎扎实实的行动去发挥创新精神。不仅仅是几个大企业要创新，更为关键的是成千上万的小企业都要参与进来，形成一个良好的科技创新环境，大家共同去创新。在这个阶段上，如何吸引人才、留住人才、运用人才，发挥区域人才储备优势，深入完善资源的互通机制，是湾区科技创新过程中的一个重要的课题。那李教授，您既是学者，也是创业者和投资人，对于培育创新科技拥有丰富的实战经验，您认为该如何打造粤港澳大湾区教育和人才高地，为大湾区科技创新协同继续输送力量了？谢谢，李教授。
谢谢主持人的邀请能够有机会在这分享这个几点看法吧。这个对于香港跟深圳也都是类似，就是一个呢，就是我们要在这个创业教育方面要这个与时俱进怎么个让这个大学的年轻人掌握了解他这个创业的这样的这个一些本事如何充分的利用深圳大湾区的这个供应链体系、产业环境资源，去为他们后面的事业服务。在疫情之前呢，我们在
香港科技大学实际上开了一门创业课程，很多学生不只是在香港的高校学习创业的理论，也来深圳，来到大湾区走访企业，了解供应链，同时跟这边的同行紧密的交流，使得他们能够了解整个这个创业的这样的一个过程。所以有相当多的这个香港高校的学生，刚刚有名主任也提到毕业后他们就来到了这个深圳创办了他们的公司这个发展也都很快这是一个这个就是从香港的这个教育到深圳的这个创业的一个过程。当然我也看到这个最近香港政府在孙局长的或者这个上任以后新一届政府推出了一系列的政策希望这个香港在这个培育新的科技企业方面能够这个有一番作为。我们也都看到了这个施政报告非常的鼓舞人心，就是前面的这些探索怎么个能够这个回馈到香港的这个创业企业的这个发展使得两地能够真正的起到1+1大于2这样一个作用。但是我相信两地的互补性，大湾区的这个创业优势就是它的迭代速度，它的迭代成本跟其他地方比都是有这个5到10倍的这样的一个优势。怎么把这些优势资源把它充分发挥出来，使得大量的这个新办的有活力的科技公司能够一批又一批的涌现出来。谢谢主持人。
好的，谢谢李教授。然后下面呢，也希望问一下 Harry， 那粤港澳大湾区的战略定位之一是要成为充满活力的世界级的城市群。那而中管那个全球最具代表性的世界级城市群的发展脉络可以发现呢，这些城市群发展离不开发达的交通通信基础，建设的网络，普惠化的那个产业政策，专业化的产业分工和协作等等。在您看来呢，海外其他世界级的城市群的发展有哪些特点和经验？那粤港澳大湾区要成为真正的世界级的城市群，还需要在哪些关键点发力？谢谢 Harry。
非常谢谢 Lisa 今天这个主持我们这样一个节目也非常高兴呢能够邀请到孙东局长有名主任一起来跟我们分享一下这深港这个科技合作这个未来的这样的一些机遇和挑战。非常高兴呢也和浙湘一起今天这个参与这样一个节目刚才 Lisa 问这个问题呢问得很好，就是讲我们这个现在我们深港我们这个大湾区这里这个和世界上的其他的这样城市集群相比，特别是这个和这个其他的一些湾区相比较，我们的优势我们的这个需要赶上去的地方到底在哪里？那大家一般讲起这个城市群和湾区呢，一般来讲呢，大家都会比较，比如讲这个纽约湾区、东京湾区和旧金山湾区这样。今天呢，就时间有限呢，我就想这是和这个旧金山湾区我们做一个比较我自己呢，因为在西雅图在这个 Silicon Valley 工作很多年呢，那边也相对比较熟悉一些。其实我们可以看比较这个 high level 来看这件事情的话，可以比如讲这个从政产学研几个角度来看这件事情。首先呢，我觉得就是说这个我们可能有优势的地方，就是说尽管我们这样的就是像香港和深圳和这个澳门其他地方这样这个广东很多的这样的这个政治体制上各方面还是有一些不一样的地方，但是相对来讲的话呢，我觉得我们香港政府我们深圳政府都非常的积极进取 相对来讲呢，就是说我们是一个这个采取一个有为政府的这样一个做法。刚才有明主任已经分享了很多这个很令人鼓舞的这样一些数字啊，待会儿我也特别想听到这个孙东局长也分享一下这个从香港这边怎么看这样这一点呢，我觉得我们其实是有很多优势的地方的。然后我们再看呢，就是学这个大学这个方面当然就是说这个旧金山湾区的话，这有一些特别优秀的学校，像 Stanford、Berkeley 这样那我们这个在我们这个大湾区这里呢，也有一批这个相当优秀的学校。当然和 Berkeley、Stanford 比，我们还有一定的差距，但是我自己也很有信心我们在这个教育方面呢，还在不断的在向前发展应该可以培养出一些非常优秀的学生这样当然，如果我们看这个产业的来讲的话呢旧金山湾区的产业的话呢，发展的早，特别是在这个 hardware、software 方面的话呢，做得非常非常的不错。但是呢，我觉得在这个我们大湾区这里呢，其实泽祥一直都分析过，就是说我们比如讲在 electronics 这些 supply chain 这里呢，我们也有自己的优势。我觉得这一方面来讲呢，可能我觉得各有优势吧。那么另外一点呢，就是在研究方面呢，其实我觉得就是我们还是有一定的差距。我觉得我们在这一些比较这个超前的这样的一些新的 disruptive technology 方面的话呢，我觉得我们可能还有很多值得我们在这个继续进步的地方。这里呢，我特别想回应一点，刚才泽祥讲的就是创业这件事情泽祥强调了，就是在这个培养学生创新创业这件事情讲得非常好。泽祥也身体力行这样这个深圳科创学院也正在这个发展当中，这个我们也充满期待。我讲一点，就是说，我觉得我们在大湾区这边发展的话，可能我们应该鼓励的一个文化的这样一个进步的地方，实际上来讲，就是和这个旧金山湾区比较。如果你看这个 Silicon Valley 很多的这样的一些 startup 的话，其实大家不要这个被这个只是出来一个 Google 出来一个 Yahoo 所欺骗了，好像都是大学生出来创业。创业的大军主力部队不是刚刚毕业的年轻大学生，甚至这个 college dropout。真正创新创业的大军的话，实际上是在工业界锻炼过来的一批人这样的。实际上是有人做过，在美国有人做过一个非科学的统计这样子这个 optimal 这个年龄这个出来创业的话，他肯定不是22岁也不是25岁，实际上这个 optimal 创新创业的年龄大约在30岁左右。所以我就想补充一下刚才泽祥那个观点谢谢丽莎，我就先讲这么多。
好吧，谢谢 Harry。然后最后呢，也希望跟问孙局长，大湾区正在建设成为国际科创的中心，那这个也给香港的创科发展迎来了很好的发展时机。我们看到香港特区政府呢，已经积极推动创科的产业，史无前例的投资了1500亿港元，用于支持科研实验室建设等项目。那包括今年5月份呢，也将我们的名称呢改成创新科技及工业局。那背后的传达是什么样的信息？这一系列的举动意义何在？然后当然刚才局长也跟我们分享了这周也刚公布的最新的施政报告，而且其实在深圳的或者在线上。也不知道我们下面呢，在主办方的整个科学园这几天呢，都有很多年轻人在下面，所以其实呢，整个心态都生态都状起来，所以其实还是香港那边呢，整个科创的生态都非常热烈的，所以反正现在也希望多听听孙局长呢跟我们分享一下，谢谢。
谢谢 Nisa。开始之前我特意跟他讲。把我放在最后一个，走了个后门，因为我想听听3位的高见，我一直在记录那现在这个回答一下这个尼瑟的问题。首先，你说为什么要改名？这改名是上届政府做的决定，我认为这个决定是英明的加了这个在原来的创新科技后面加上工业从某种情况来看呢，实际上呼应了我们这届政府提出的这个方向，就是以结果为目标。因为香港回归20多年，我们谈了很多科创但是我们一直究竟要为什么那么现在呢，就是本届政府明确提出要以产业作为一个重要的一个发展的一个考量。实际上这次呢 特首的施政报告。那么我们在谈到经济发展的时候呢，也特别强调重视这个创科的产业的发展。那为什么要强调创科产业的发展？有几个原因。第一个原因，实际上是为了巩固和提升我们现有的基础科研的优势。我们香港的这个，我认为是最宝贵的资源，就是我们的基础科研的优势。我们几所大学，一个非常不错的大学。那么这些大学，这是基础科研，这些科学家是我们香港现在提出要建立国际创新科技中心的底气所在。但是大家都知道，这些年我们的投入一直不够的。您刚才说我们上届政府投了1500亿，那么1000多亿都去了基建，真正到了前线的这个科学家手里呢，可能也就500亿，不超过600亿。那么呼吁很多年，那钱从哪里来呢？这个从内地看啊，这个我们大湾区基本上在3%到4%，它大部分钱都来自于产业界，是产业的发展。那么香港政府再怎么投，再怎么有钱，它也不会投到3%到4%。现在我们目标是投到1.5%，那么就要很困难，因为我们的医疗、我们的福利、我们的住屋、房屋都需要钱。所以从这点来讲的话呢，我们需要产业支持香港的科研，支持香港的大学。那么从另外一方面来讲的话，只有我们产业的发展，才能把人才聚集起来。我们大学跟产业才能互动，才能推动香港的科研上一个更高的层次，我们才能真正做大项目。所以这个是我们有这个重点的考量。另外一个考量就是我们香港社会的呼声也很强烈，因为下一步搞国际创新科技中心，虽然我们对科研界的钱投的不多，但是在香港社会很多人看也是投了很多钱了，你有什么产出啊？对香港社会有什么贡献呢？等等，我们这方面压力也很大。那么我们下一步怎么样利用科技呢？能够为香港的经济增长 GDP 能够增加几个百分点，能够为香港年轻人的就业多创造点机会。所以综合的考量，我们就提出要做科技产业。但是大家注意到没有，我们即使做科技产业，比如说这次我们提出来产学研1+计划，我们还是紧紧围绕着我们基础科研的，因为我们的前提是大学的这些团队以前要有比较好的基础科研的成果，我们希望把这些优秀的科研成果转化落地，然后再商品化。所以整个来讲是这样一个这个基本的思路。那么未来我们对基础科研很重视啊。今天我谈的比较多基础科研，因为我们是科学论坛嘛这个基础科研，我觉得我们在座的科学家也要思考香港应该怎么搞。我们以前不是没试过，几年以前徐院长在，我们投了100亿做英东航港当然我们还要继续做下去。那么我们2GC 每年也投了不少钱，当然相对内地来讲少很多，但是也在做。那么下一步香港这个基础科研，我们怎么样上一个更高的台阶，搞一个更高的形式？我觉得我们在座应该思考一下。我觉得现在我们从内地来讲，有些经验是可以借鉴的，比如说他搞863，搞973，它是针对某一个科学的前沿一个主题，那么组织相关的资源去做。美国、欧洲都有类似的计划。我记得几年以前，徐立之教授也提过，我们能不能把一些各个高校，比如说您是做生物科技生物医学科技，能不能打破学校之间的壁垒，然后做一个整合，类似这种，我觉得这些 idea 是可以借鉴的。要有主题研究，针对某一个主题。你比如说，我们想搞电子的微电子，搞芯片，有没有可能结合香港整体的优势，搞一个主题计划，一投20亿、50亿下去？那么我们尽管要搞基础科研，除了现有的以外，我觉得今后新的形式我们要思考，要整合起来做大项目这个呢，所以我希望未来2-3年以后，我们有机会再拿到一笔新的资源，把我们的基础科研再做得更高更强。好，谢谢。
好，谢谢局长。那就因为剩下的时间也不多，那我先问一下，在场有没有人有什么问题？香港的或者深圳？先给你们一个机会，因为其实我自己很多问题的。对，香港那边没有，深圳、线上那边没有。那我如果是这样的话，我可不可以问一个问题？那这个不在本来我们的稿子里面的，但我想到今天有这么难得的一个机会，我们都有香港的，还有深圳的那个我们那边的一些 高管呢，那也希望听听。我的问题说，就是你们各位觉得5年后，我们今天也谈了那个粤港澳大湾区，5年后我们怎么样衡量是不是成功？那个成功是应该是可以做到什么的一个成果呢？那要不我先问一下，那个深圳的王主任，要不我们按照这个来，您可不可以跟我们分享一下，你觉得5年后的怎么样才是成功？
谢谢这个主持人，这个问题非常好啊。这个我们现在谈合作，展望一下5年之后，到底什么样才叫成功了？我想啊，这个成功这个有这么几个标志。第一个呢，就是我们2个地方啊，这个深港合作，包括这个粤港澳大湾区当中深港这2个城市的这个合作，应该成为粤港澳大湾区最重要的创新引擎。这个标志性的这个功能有没有发挥出来啊？因为刚才这个Harry 也讲到，这个全球有一个创新评价的这个湾区的评价是香港、深圳、广州的这个产业集群号称是创新的第2名。那么这个城市之间的合作，特别是港深之间合作，能不能再进一步的提升，这是一个标志。第二个呢，就是能不能这个把香港这个连通世界的这种连通世界市场，加上深圳的这种产业转化这种能力能不能有效的发挥出来，使得深圳的创新型的企业进一步的成长。第3个呢，就是我们的这个高校这个培养人才，包括在学科的这个建设上这个有没有在进一步的提升？因为这个也都有一个综合的评价。第4个呢，标志呢，就是能不能聚集世界顶尖的一流科学家和人才，特别是有更多的年轻的这个顶尖这个科学家能聚集到深港这个姐妹城当中来。我想从这么4个要素来做一个衡量，不知是否妥当啊？
好啊，谢谢。那直向呢？那个刘教授，你跟我们也可以分享一下吗？
对，我蛮认可刚刚这个孙东讲的以结果为导向也许5年后、10年后，就是一些以科技为支撑的品牌全世界这个知名点能否出现在大湾区而且是通过这个深港大湾区城市之间的紧密合作产生的。
好啊，谢谢。那 Harry 呢？
对，我觉得这个，因为我自己在工业界工作这样我觉得这个其实这个一直都大家都要搞清楚这个最后这个目标是什么。但5年呢，其实是一个很 tricky 的时间，就是说这个做一个产业来讲的话呢，其实5年的话呢，时间是远远不够的。我觉得5年的时间的话呢，如果我们能够深港合作，能够基本上可以看得到，比如讲这种新兴的一个产业能够形成一个这样的一个雏形，这样这个所以我想就可能是一个比较这个 realistic 的这样的一个 metric 我是这么看的，就是我们通过我们深港科技合作，在某一个方向某一个产业5年可以看到，就是说这个可以真正我们可以 own 这样一个 area。
好啊，对，那勋局呢？
实际上我们在刚刚公布的施政报告提出了很多目标指标，我就不在这里一一赘述。但实际上我们谈到香港的创科发展，我们已经清晰地点明4大方向。第一个就是完善创科生态圈，实现再工业化。那么这里面有很多指标那么5年内现在大家认为5年不可能都实现一个多么辉煌的产业的企业，但是可以看到它基本的雏形 那么起码我们这个 GDP 制造业的 GDP 在增长的路上啊。那么第二个呢，就是我们其中一个发展方向就是要丰富创科人才库，增加发展动能。那么这个抢人才、抢企业是我们这次施政报告的一个重点。那么我希望5年以后，我们香港的这个人才的情况要比现在呢要有很大的改善。实际上，特首施政报告公布的当天晚上，我就接到了一些查询，我们这个内地的学生在 MIT 要毕业，说打算要回来，他们就想到了香港等等。我相信，只要我们把社会氛围营造好，是在海外的很多华人，包括我们香港自己的学生内地的学子他们都会到香港来，因为香港政治稳定。因为这些人来，当然我们说免印花税待遇等等，但是真正很多优秀的人才看重的是在香港工作的机会。所以我特别同意我们李家超特首说的，香港就有天然的 DNA 吸引世界的人才过来，我坚信不疑那么第三个，我们要做叫建智慧城市。今天这里我就不说太多了。智慧城市一个重要的指标，我们要搞智慧政府，2年内要全部电子的这个政府服务要电子化上网，3年内要用一网通办，我们的这个智方便等等，就是为了给市民要创造各种方便和方便那么第4个方向呢，就是我们要融入国家发展大局，一个重要的指标，我们跟深圳的合作河套能不能起来？我们现在的目标是本届政府内河套一定要投入运营这是我们是这个下定了决心，虽然公开没有讲，我不知道今天有没有媒体但是这是我们内的目标，一定要投入运营这个王永平主任也都在内。好，我这是谈这些观点。
好的，非常感谢4位的我们时间那边已经到了，短短的时间内我们谈得非常深入的粤港澳大湾区的一个讨论。那我们给我们4位嘉宾呢很热烈的掌声吧，感谢他们，谢谢大家。好，谢谢。
Thank you for the sharing again. Please be seated. Our technical sections have now complete. Before we end the symposium, may I invite Mr. David Yu and Professor Lap Chi Choi to share their closing remark. We first invite Mr. David Yu, Chairman, 2022 Future Science Prize Donors Congress, co-founder, and Chairman of Yu Feng Capital, Chairman of YF Life Insurance International Limited, member of the board of Fudan University, to come on stage to deliver his remarks. Mr. Yu, please.
Thank 尊敬的各位来宾，大家下午好。我是未来科学大奖捐赠人大会2022年轮值主席于峰，来自云峰基金。很荣幸代表14位捐赠人参与此次活动，并致闭幕词。首先感谢徐立之教授和沈向阳博士发起的本次活动，感谢科学委员会策划议程，并邀请了这么多世界顶级的科学家。请允许我代表未来科学大奖，对在香港会场、深圳会场以及线上参加的所有嘉宾表示由衷的感谢。今天，众位杰出的科学家在生命科学、物质科学、数学和计算机科学领域的前沿分享，为听众们带来了一场精彩绝伦的科学盛宴，让我们领略了科学的独特魅力，也为我们如何构建未来世界提供了新的思考角度和方式。相信科学家们在科研工作中的突破创新和坚持不懈的科研精神，会激励广大青年科研工作者们去探索更多未知的领域。今年正值香港回归25周年，也是未来科学大奖基金会与香港科学院的首度合作。未来科学大奖自2016年设立以来，共评选出了27位卓越成就的科学获奖者，获得了世界及社会各界的广泛关注和好评。 参加今天峰会的就有8位未来科学奖的获得者，他们是卢玉敏教授、袁国勇教授、陆锦标教授、薛其坤教授、马大为教授、杨学明教授、林本坚教授、莫一鸣教授。这些获奖者是由国际科学界共同参与评选出的，代表了当下国际前沿的顶尖科研水平。一直以来，香港对国际创新科研资源和高科技人才保持着极大的吸引力，在基础研究、国际资本、法律制度、营商环境、国际创新资源等方面具有独特的优势。未来，香港作为卓越的创新科研中心，不仅会继续发挥对外开放和国际交流的窗口作用，还承载着粤港澳大湾区与内地城市的珠联璧合，强化产学科研的协同，建设全球科技创新高地的关键使命担当。未来科学大奖希望能够与粤港澳大湾区的高等院校、科研机构、科学公益组织合作，举办不同形式的科学交流活动，建立更深层次的联系，为香港建设全球科技创新高地和粤港澳大湾区协同发展贡献智慧和力量。正如今天的论坛的主题所言，科学见未来，科学发展是不断去探索世界的边界，创造更广阔的未来。作为投资人、创业者，我们陪伴了许多杰出的企业家，同时我们也希望未来能有更多的机会陪伴许多的科学家，陪伴他们一起走过漫长的、充满挑战的科研道路，因为我们相信科学的力量定能让明天让这个世界更加美好。这里我也回应刚刚孙东局长说的，我们也希望能够在这个为香港的在科研基础科学和产业的结合上，能够更紧密的合作，贡献我们自己的一份力量。谢谢大家。
Thank you, Mr. Yu. Now, please welcome Professor Lap Chi Choi to give our closing remark. Professor Choi, please.
Hello, everyone. What a wonderful day. Truly, I was overwhelmed. And it's truly a rare occasion that we assemble so many people, both scientists and leaders of society, to come together to talk about how science can change and shape the future. And we had took a lot of notes, but in scrap papers, so to find them. I think we actually heard a lot of new paradigms being created, and also we heard the beauty and the impact of fundamental physical science. And we saw the power of mathematics and computer science. Finally, we also heard how Shenzhen and Hong Kong can collaborate and cooperate. So a lot of food for thought. But I'm sorry to say that we have a little technical problem in a connection with Dr. Bernlin. So we only heard half of his talk, but we'll improve on that. So what's left for me to say is I really have to thank Harry, for coming up with this idea, holding this future forum in Hong Kong. We call it Hong Kong Symposium. And I would like to again thank all the speakers, all the contributors, the panelists, and then especially Ji Zhang. Yeah, he came back to participate in the last session, and his support in science and technology in Hong Kong. And last, I'd like to thank all the people who are still here. I think they're all still in Shenzhen too. but I cannot see them here. And thank you all for joining this wonderful day. And I myself, in my opinion, that the Hong Kong Symposium has been a great success. I really hope that we can have such high power discussion and views shared in more frequently. And now really every good thing has come to an end, and I declare this symposium closed.
Thank you, Professor Cho. Ladies and gentlemen, our symposium has come to an end. Thank you once again for joining us, and I hope you have enjoyed it. For guests holding e-tickets for the symposium banquets, we have arranged shuttle buses to take you to the Hyatt Regency Hong Kong Sha Tin Hotel. The first bus will leave at 18:10 and the second at 18:20. Our helpers will show you the way to the buses. Please follow the signs and their direction. We have already allocated the seats for you at the banquet. Our helpers there will help you find your seats. The dinner will start at 18:30. See you there. For all of you, have a wonderful evening. Thank you.